I want to talk to y'all about oxidation-reduction reactions. This is our third type of reaction that occurs in aqueous solutions. Oxidation numbers are numbers that provide us a way to keep track of the electrons, where they transferred to during the redox reaction. So let's talk a little bit about what a redox reaction is, and then the rules for assigning oxidation numbers as well. Oxidation-reduction reactions are referred to as redox reactions because they occur hand in hand. If there's an oxidation reaction occurring, there's a reduction process also taking place. These are reactions in which one or more electrons are transferred. So in order to figure out who the electrons are transferred to and where they came from, we do need to understand the rules for assigning oxidation numbers. These are also referred to as oxidation states. These provide us a way of keeping track of the electrons in the redox reactions. So the rules for assigning oxidation numbers, first rule, and these are in hierarchical order, atoms in the elemental form, which means they're uncombined, they always have an oxidation number of 0. Keep in mind, atoms are neutral. So if you just have in a reaction sodium atom or oxygen in its elemental form, diatomic oxygen, or mercury, not in a compound, its oxidation number will be assigned as 0. If you have a monatomic ion, like in our net ionic equations we've been looking at in a monatomic ion, the oxidation number of the monatomic ion is equal to the charge of the ion. So here you see the potassium ion. You would assign that, if you saw it in a net ionic equation, as a +1. The nitride ion would have an oxidation number of -3. The next rule applies to fluorine. Fluorine's oxidation number is always a -1. Now, sort of a rule of thumb with these is that their oxidation numbers are going to be equal to the charge that they normally would form as an ion for the most part. And again, these are hierarchical, so fluorine gets precedence over any other element. The group 1A elements, their oxidation numbers are always +1. Keep in mind, those elements typically form a +1 charge when we're assigning their charges to write the ionic formula. Group 2A elements are +2. The group 7A elements are -1. These are our halogens. Now, oxygen has a couple of rules. In most compounds, oxygen is going to be assigned an oxidation number of -2. Now, keep in mind, these oxidation numbers are if they're in a compound. Remember, compounds are neutral. So if they're in a compound and you're trying to assign your oxidation numbers, -2 for oxygen normally. However, if oxygen happens to be paired up with fluorine, since fluorine gets precedence, you would assign oxygen's oxidation number as a +2. There are 2 polyatomic ions that contain oxygen. One is the peroxide ion, and then you have the superoxide. So here's the formula for each. And so in the peroxide ion, the oxidation number of oxygen is a -1. Let me just kind of explain why that is. In the formula O2, -2, some of the oxidation numbers have to add up to the charge of this polyatomic ion. So since there's 2 oxygens here, let me kind of draw a line here. The 2 oxygens, 2 times what will give you a -2? Well, 2 times a -1 would give you a -2. With the superoxide, now this one you don't see a whole lot, but notice that the charge of this polyatomic ion is -1. So since there's 2 oxygens here, and the sum of the ions have to add up to the charge, the sum of the oxidation numbers have to add up to the charge of the ion. Now, these are not coming in order. I'm sorry. Okay, there you go. -1/2 is the oxidation number you would assign to oxygen if it's a superoxide. Again, The reason is because there's 2 oxygens here, and the sum of the oxidation numbers have to add up to a -1 because that's the charge of the superoxide ion. So you have a half a piece. And again, this is very uncommon that you would see this, but if you were to see the superoxide ion in a compound, 2 times a -1/2 will give you -1, and so that's why you get a -1/2 each. Okay, hydrogen. If hydrogen is with a more electronegative element than he is, now remember, electronegativity as you go up and across the periodic table increases, and hydrogen's electronegativity is a 2.1. Now, if hydrogen is with a more electronegative element, for example, if he's with fluorine, HF. Now, we know fluorine automatically gets a -1 oxidation number assigned to him. So since the sum of your oxidation numbers in a neutral compound have to add up to 0, hydrogen would have to be a +1 here because +1 and -1 equals 0. So if hydrogen's with a more electronegative element, he gets assigned a +1 oxidation number. Now, if he's with a less electronegative element than he is, such as if he's with a metal, sodium and hydrogen will give you sodium hydride. Well, keep in mind these rules are hierarchical, and the sum of your oxidation numbers in a neutral compound has to be 0 because they're neutral. We have a rule for sodium up here, +1. So sodium would get the precedence, +1, so that means hydrogen has to be a -1. +1 minus 1 equals 0. Now, those are the only elements that have specific rules. So if you happen to have an element in a compound that does not have a rule for it, you have to assign oxidation numbers for the elements that do have rules, and then solve for X to figure out the oxidation number of the remaining element. Now, as I've already mentioned, the sum of the oxidation numbers in a compound have to add up to 0. And if you happen to have a polyatomic ion, like with your net ionic equations, the sum of the oxidation number in the polyatomic ion equals the charge of the ion. So let's do a couple of examples here. Here we have neutral compound water. So I'm going to come over to the side and explain this as we go. Since this is neutral, I know the sum of the oxidation numbers have to add up to 0. So you want to see, is there a rule for either of these elements? And then you have to assign the oxidation numbers in order of their rules. So the oxygen rule came first. So oxygen in most compounds is a -2. So there's one oxygen here. 1 times a -2 gives you a -2 for the oxygen total charge here. So then you got to figure out what hydrogen has to be here. So to make this equal to 0, we know the total hydrogen oxidation numbers have to add up to a +2 because a +2 and a -2 equals 0. Now, since there's 2 hydrogens here, you have to take that into account. So that means each hydrogen must be a +1 apiece. 2 times a +1 gives you a +2. So you would say hydrogen's oxidation number is a +1 and oxygen's is a -2. In ammonium, this is a polyatomic ion, so NH4, and the overall charge here is a +1 for the polyatomic ion. That means the sum of these oxidation numbers have to add up to +1. Well, nitrogen does not have a rule, but hydrogen does. And so nitrogen happens to be more electronegative than hydrogen if you look at their position on the periodic table. So hydrogen in this case here is going to be, since he's with a more electronegative element, it's going to be a +1. So 4 times a +1 gives you a +4 overall. So now you have to figure out what number when added to +4 equals +1. So that would have to be a -3. 3 plus 4 is +1. Now look down here. How many nitrogens do you have? Well, there's only one nitrogen. So that means that the oxidation number for that one nitrogen is a -3. So you would come over and assign it, -3 for the nitrogen, +1 for the hydrogen. Okay, you try these two, pause the video, and then check your answers. I'm going to go ahead and complete it. So for oxygen, this is a neutral compound, first of all, so the sum have to add up to 0. And there's not a rule for carbon, but there is a rule for oxygen. Oxygen, as most compounds, is a -2. So 2 times a -2 gives you a -4, and that means the carbon must be a +4 to make that equal to 0. And there's only one carbon here, so you would say carbon is a +4. Oxygen, in this case, is a -2 because you got to look at each individual oxygens. Okay? Nitrate. These have to add up to -1 because it's a polyatomic ion, the charge of -1. Nitrogen does not have a rule. Oxygen does. Most compound, he said a -2. So we're going to go ahead and assign him here a -2. So 3 times a negative 2 gives you a negative 6. So what number, when added to negative 6, equals negative 1? Well, it has to be